Right triangle trigonometry, case study. Let's look at case A. We have two sides that are known. The hypotenuse, 13 meters. The adjacent side, 5 meters. Our task is to find the rest of the sides and angles. Find all sides and angles. Okay, here's our scaled down right triangle. Well, the first thing I'm going to do is try to find the opposite side. And we're going to employ the Pythagorean theorem for that. So what we know from before is that the hypotenuse squared equals the adjacent side squared plus the opposite side squared. So what I want to do is solve for the opposite side. I'm going to do that using our friend SADMEP from algebra. So I'm going to subtract adjacent to the other side and isolate opposite, at least opposite squared. So it's going to look like this. I'm just going to section it off over here. Opposite squared equals hypotenuse squared minus adjacent squared. Now, of course, that's opposite squared. I want to know what the opposite side is, and so I've actually got to take the square root of both sides. So I'll do that in nifty blue marker here. Square root of the left side and the square root of the right side. It's the entire thing that's the square rooted. Remember that. It's always the entire thing, expression that is going to be square rooted when you take the square root of both sides. So it's the contents of this, and then you square root it to evaluate. So I think we can do that now. So we have opposite equal to, we're ready to substitute the values in at this point. We've done our symbolic algebra. So it's the square root of 13 squared, and that's meters, right? Like so, 13, actually, you know what I'm going to do? 13, put it in parentheses. It's always much better to do that. It looks so much better. 13 meters, if I want to include the unit, I'll put that in parentheses. Squared minus 5 meters squared. All right, so what we have is that the opposite side is equal to the square root of 169, and that's meters squared here, minus 5 squared, which is 25 meters squared. Let's extend that across. Okay, well, 169 minus 25 happens to be 144, which is a nice number for us. You'll see why in a moment. So the opposite side is equal to the square root of 144 meters squared, which is actually equal to 12 meters. Right on. The square root of meter squared is just meters, and the square root of 144 is 12. This is a very well-known triangle known as the 5, 12, 13 triangle. I'm sure it has a fancier name in mathematics, but I like it. 5, 12, 13. It's very easy to remember. Hike! All right. That is cool. We have all the sides. We now have the adjacent side from given information, 5 meters. The hypotenuse was given as 13 meters, and the opposite side is 12 meters. Well, we still need the angles. How are we going to get them? Okay. For now, we're going to use another friend known as SOHCAHTOA. Okay. I'm going to just kind of region off a little area here. It's slightly separate so that we can organize the board. And SOHCAHTOA is an acronym. It's an acronym. And I'll show you what it stands for. SOHCAHTOA. Okay? It's a relationship between 3 trigonometric functions and the ratio of the sides of the right triangle. So we have sine of the angle is equal to the opposite side over the hypotenuse. We have the cosine of the angle equal to the adjacent side over the hypotenuse. And then the last trigonometric function is the tangent. Tangent, well, the last one that we're using anyway, is opposite over adjacent. Okay, these are ratios, and I need to put the angle in there like that. Tangent theta. Remember, we learned theta from before as a Greek letter. It symbolizes angle, in this case, angle, angle. And so we can use this because we have all sides. We have the opposite side, we have the hypotenuse, we have adjacent, we have hypotenuse, we have opposite, we have all of them. It's terrific. So what I'm going to do is try to find the adjacent angle, okay? So what we need to do is find something with the adjacent in it. And so we got two choices. We have the cosine as adjacent, and we have the tangent. Either one would be fine because we have all the sides. So I'm just going to arbitrarily choose one of them, and I'm going to go with cosine. All right, so here's how we set it up. The cosine of the angle is equal to the adjacent side over the hypotenuse. Those are the ones that are given, so I prefer kind of going with it. That's why I chose cosine, but you're free to choose the other once you have them all the sides. Cosine theta is equal to adjacent, which is 5 meters, divided by the hypotenuse, 13 meters. So here's our ratio. 5 over 13 is the cosine of this angle. Well, we have the cosine of the angle, which we can find pretty niftily from any scientific calculator. You'll notice that there's a series of buttons right here that have sine, cosine, etc. And the thing is, we're actually going to use what's called an inverse trigonometric function to get the angle, because it's almost like a reverse lookup. If we have the ratio of these two sides, we can use the calculator to kind of do a reverse lookup for what angle subtends this ratio. Okay, so we're looking for this. Yay! We're looking for the angle that will hug the opposite side. Or yes, we're looking for the opposite side in this case. But no, that opposite side is given. Sorry, the adjacent angle, which the adjacent angle does hug the opposite side, so it's kind of true. So here's what we got to do. Very important. You might notice that this is a statement down here. Set calculator to degree mode. If you've noticed in the classroom, there are some flyers and posters around that say set your calculator to degree mode. It's kind of important. You know, don't freeze, set your calculator to degrees, all these great slogans. And let me show you quickly how to do that here on this calculator, right? There's a button, once we get it focused, right here called DIRG. Might be mode on your calculator if you got a fancy calculator. I'm gonna hit DIRG, and look, we have some choices. Deg, rad, gird. They stand for degrees, radians, and gradients. And degrees is what we want. It just divides a circle into 360 degrees for full rotation. That's fine. We'll look at some of the other ones another time. We really will use degrees most often. So set your calculator to degree mode. Okay, now that I know mine is, we're going to run this calculation. I have to solve this kind of for the angle. So I'm going to do that. Here we go. You would think that if you're solving for this angle, you would divide by cosine. It doesn't work that way with trig functions. It's just one of those weird things. So we'll make that a little bit of an exception. But here's how we do it. We take the angle, and what we do is we say that's equal to the inverse cosine. So that is what you'll find on your calculator. It'll probably say cos -1 or something like that. And I'm pointing at it right here, cos. And right at top is cos -1, so I got to go to the second function to grab it. Which, obviously, anything to the negative first power is 1 over cosine, but it's not really 1 over cosine. Again, it's just one of those, it's written this way, but it's really called inverse cosine, all right? Or maybe arc cosine and other vernacular. But here we go. Cosine to the -1, the inverse cosine, of 5 meters divided by 13 meters. Now you notice in a ratio, if you have the same units, units just cancel. So it's just a ratio. An angle doesn't really care about the units as long as they're the same, because it's just looking for the units to cancel anyway as a ratio. All right, now if we do this, alas, type it in here, I will do it so that you can see, all right, what it looks like in this calculator. Aha, second. Cosine negative 1, 5 divided by 13, like this. So it's going to look like, yay, with some glare. There we go. 5 divided by 13, cosine negative 1 equals about 67.3 degrees is what it says. Okay, that's fine. 67.3, that sounds about right, actually. We'll talk about why that's logical in a little bit. 67.04, if I round it up, degrees. All right, good. Well, we would expect that if these angles all add up to 180, and this is always 90, then the sum of the opposite angle and the sum of this adjacent angle over here is going to be, it's going to be 90. And so the bigger angle right here, this bigger angle, 67.4 degrees, has to subtend the bigger side, which is 12 versus 5. So this angle up here is going to be narrower, and this one's going to be larger. So we have 67.4 degrees, and that's close to 90. So, good. We have the opposite, we have this adjacent angle over here, the one that's next to adjacent. We'll get the one that's next to opposite. Simply, we can do that through SOHCAHTOA, but we're going to do it a better way. We're just going to subtract 90 minus 67.4 equals the angle that we're looking for up here. And then we'll have them. We'll have everything. We'll have all sides and angles. Not bad. It fits on one board. How cool is that? All right, 90 minus 67.4 gives us the 22.6. Totally reasonable. All right, 22.6 degrees. All right, that's for the opposite angle over here, the one that's up here, called the opposite. And this one's next to the adjacent side. Okay. And this one was la la la. Good. What I'm going to do next in another video is go over a case where we're not given two sides, but we're actually given a side and angle, and we'll run through the case again with trying to find all sides and angles. Whew. All right, we got through it. And so what we'll see is how we can use this stuff to model motion and look at vectors in displacement, look at vectors in velocity, and even something called acceleration, which we'll get to shortly. More ad. Over, out.